So we'll say that this is mass hung. This is mass of car. Later on, we can put in like 20 grams or 500 grams. Let's work from this standpoint. Let's also, to simplify our discussion today, we'll start with the problem in which the coefficient of friction is 0. Now, I'm starting with this problem because it's one that's tangible and one that you guys have used already. But there are things about this problem that are going to be challenging for us. So let's handle a couple of them. For example, would you agree that this system is going to accelerate in its current state? And can we all agree that the acceleration will be this way? I'm putting the arrow over where the pulley is. And the reason is because you're going to have to start adding a step. And this might be a step to add from the very beginning. Remember when I said you want to choose an axis that is aligned with the positive direction of acceleration, or make that your positive axis. You've heard me say that a couple times already, that's one of your priorities. We know that this is a net force equals ma problem. And we know it's going to accelerate. When you have to choose your coordinate system, I've asked you to pick a coordinate system where your priorities line up with the acceleration. But that's different things to different masses here. I think we can all agree that this mass is going to accelerate this way, and this mass is going to accelerate that way. I want this to be the positive direction here, and I want this to be the positive direction here. So I will often label a pulley with its positive direction and say that that's the positive direction for all the objects connected by the pulley. You can imagine a true Atwood machine. This is called a modified Atwood machine. But a true Atwood machine is just two weights on either side of a pulley. You release that, one likely goes up and the other goes down. But we want a unified direction for positive. The next question I have for you I think is easy, but third period proved me wrong. Can we say that the acceleration of this car is the same as the acceleration of this weight? Do you have reason to believe it's true? Now, I know you're just saying that, but don't discount it out of hand. There's a way to prove it's true. A simple analogy. If this box moves 10 centimeters, you understand that, does this box move 10 centimeters? That's a good question to ask. That doesn't have to be true. Acceleration is easy to do. Make sure you discuss that, you think about it before you start your problem. And yes, I think we can say that these both have the same acceleration. Now, the first thing I know that you would expect me to say is you should probably start a free body diagram, start dealing with diagramming this problem out. I think we can start making some changes or modifications to the way in which we do a free body diagram. For example, if I start a free body diagram for, say, the weight hung, at its simplest form, you guys had what, 20 grams on the edge and maybe 500 grams on the table? That was probably one of the possible data points you had. 20 grams is 0.2 newtons. So if I say that the weight downwards is 0.2 newtons, and I'm trying to be consistent about the size of the arrows I choose in my free body diagram, and I say this is mass hung times g, can I draw an arrow for the car's weight that is reasonable in size to the one I've just drawn? This is supposed to be 0.2 units long. The car is 500 grams. That's 5 newtons. The ratio of 5 to 0.2, I would have to have an arrow that's, well, bigger than the board, right? But keep this in mind and start thinking this way. Do I need to worry about the up and down forces for the car? I mean, the up and down forces relate normal to the weight of the car. Do I need the normal force for this problem if there's no friction? I don't think that I do. So although a true free body diagram, when asked, should represent all of the forces, for this diagram, I can't draw it to scale, so I'm only going to worry about the ones that matter. And the one that matters is that this car is experiencing a tension force that's in this direction. Don't draw it yet. I didn't put the arrow on there. Don't draw it yet. I have to start getting your diagrams to be more reflective of the actual thing that's happening. The only way the weight accelerates downwards is if the tension force it's experiencing is less than the weight. It took a long time to get there, but that was the result of our conversation over here, correct? So I need to make an arrow for tension that is less than the size of the weight. Now, does this box have a tension that is the same size as this tension? Are these a Newton's third law pair? This is a harder question than it sounds because you don't have enough information to make this decision. So, are the objects in contact here? No. And so this is not a true Newton's third law pair. We have to add a step because there's a pulley. Pulleys do require a bit of analysis. There is a upwards tension in the rope, this is true. But that acts on the pulley. We know there's a sideways tension on the car. We saw the car move. The Newton's third law pair also acts on the pulley. The pulley is experiencing at least these two forces, but that's not it. If it was only those forces, then the pulley would probably be accelerating. The pulley is also mounted with an axis in the middle and a spindle. So there's another applied force on the pulley to keep it in place. Well, that's why the net force on the pulley is 0, because the pulley didn't go anywhere. Now here's the important question, the one that I need you to be thinking about. Are these two tensions the same? And this is where you don't have the information that you need. Those two tensions are only the same if the pulley has no inertia. Now, how do you know? You have to be looking for something. If I tell you that the pulley is massless, or nearly massless, then I'm telling you that the pulley has no inertia. If the pulley has mass, those two are not equal, because it will take an unbalanced force to turn the pulley. But if the pulley is massless, it doesn't take an unbalanced force to turn it. This is a weird little idea here, and I don't want to complicate things more than necessary. But if our pulley is massless, it merely redirects tension. And we can treat these two as a third law pair. I have to be careful about saying it this way because second semester the pulleys get mass and we have to deal with this problem. So first semester the pulleys can stay massless and our problems can be easy, easier. Second semester we change out all the pulleys for massive pulleys and we have to deal with the fact that these are no longer the same. Does everybody understand? Put in your notes this way, look for the word massless. I'm training you on what to look for to know whether your pulleys have inertia or not. They'll have to say it's a massless pulley. If it's a massless pulley, the tension is the same everywhere in the cable. The moment the pulleys have mass, the tension is different on either side of the pulley. Now, handled a lot. The execution of this problem isn't terrible. It's a net force equals MA problem. So tension equals mass of car times acceleration. Remember, this is the stuff that's on your test. Right? I'm doing the same things. If you couldn't have written T equals MC times A, you're going to fail your next test. Some of you couldn't write that on the last test. This is why I'm saying you're getting your test questions now. The mass that's being hung, remember, I'm trying to make sure positive remains consistent for both sides. So I'm going to say MHG minus tension equals MHA. Net force equals MA. But this is acting on the hanging weight. This one's acting on the car. Newton's laws give us two relationships that could probably be used to analyze our system. These are our two relationships. I'm noticing something about these two relationships. I don't know about you, but I have a positive T here and a negative T there. Are you guys seeing that? Seems like I could easily put these things together and eliminate T. One thing I would encourage you to start doing is stacking these. We're going to have sometimes 2 or 3 of these. Look for the things that will cancel out. Do you see that if I add these 2 relationships together, the t's cancel out? This is a different way of doing this besides substitution. So let's just get all that distraction out of the way and realize if I have these 2 relationships, that I can use just simple addition to add these 2 things together. Add on the left side, and I just get MH times G. Right, the 2 T's will sum together to be 0. Add on the right side, and I get MHA plus MCA. Factor out the A's. I'm doing more math than I normally would and more steps because after looking through some of your tests, some of you are still having some trouble with all the letters and the algebra. So I'm spending a little bit more time. Now that I factored out the A, I can isolate the A. Does everybody see what I've done here? Any questions about the math? Physics got us to here. I just thought it might be nice to figure out what the acceleration is. I have 2 goals for our discussion here. The first is to see if this is in line with what you did in your lab. In your lab, you might have hung 20 grams and had a car of 500 grams. I put it all in kilograms. Is this in line with the kind of numbers you had from your data? Figure it out. It's 0.2 divided by 0.52 times 9.8. Yeah.
Why did you put the G on the outside?
I put it on the outside of the equation for this purpose. If you look at everything in here is about the masses that were hung, right? It's also to show you that the top is in units of kilograms and the bottom is in units of kilograms, which means this is unitless. It's just a percentage that scales the G. G is an acceleration of gravity. So this is a way for me to signal to you that I have a value here that's going to be in the correct units for your answer. Does that make sense?
Yeah.
And so that's why I collected them.
Okay.
There's no other reason besides that, just to kind of clarify that part. What do you get, 0.3 something? Is that in line with the kind of numbers you had in your lab? 0.3s and 0.2s and stuff like that? If you'll notice, this is probably one of the higher accelerations that you should have gotten if you hang 20 grams. I say that because this number only got bigger and bigger throughout your lab, right? You kept making the car more massive. But the mass that you hung should have stayed the same the whole time, right? I have one more observation to make, and that is we could figure out what the tension's supposed to be, can't we? I could plug this back in and figure out an expression for the tension that has to do with the masses. I want to do that next. So tension equals mH over mH plus mc times G, all times mc. I put the A first. I know I shouldn't have. So let me move that around because I don't want to be asked why I did it. There. I did this on purpose, but can I reorganize it a little bit? Just a little bit. So I just moved this one outside and this one inside. Okay? This is the weight that was hung. I told you in your lab that that was what was causing the tension. I also told you that that wasn't going to be exactly true. You see this number, right? Do you notice that that number is really close to 1? The top is the mass of the car, say 500 grams. What's the bottom? The mass of the car plus the mass hung. Right? Pretty close to 1. But does it stay the same all the time? When I put an extra 500 grams in the car, you notice that number changes, right? If I put 1,500 grams in the car, number changes even more. You notice that it's close to 1 all the time, but it's never exactly 1. This might be one reason why your tensions aren't working out perfectly in your lab. But notice they're pretty close to 1. All right, bye-bye. Consider for just argument's sake a different problem that's more straightforward on that question. I push on the blue box with some external force. And again, let's rule out friction. Will both boxes move to the side? Will they both have the same acceleration? Unless the blue box is being crushed by the green box, they should both have the same acceleration. The green box can't accelerate faster than the blue box because then they would separate, right? So I think it's not unreasonable they both have the same acceleration. The force is acting on the blue box. Pretty easy to draw. External force to the side. What else? Two normal forces, so a normal force from the ground and the weight. And there's another normal force to the left. Arguably going to be less than the external force because I think it's going to accelerate to the right. I would probably call this the force on the blue box from the green box. So wouldn't there also have to be a force on the green box from the blue box? Those are a clear Newton's third law pair. The boxes are in contact.